Hey everyone, welcome to day 24 of Math 133. Today we're going to be working on the Chapter 10 project, and then if we have time, we'll start working on the sample final exam. So our final exam is on December 11th, but we're going to cover the sample final exam on December 9th. But it's pretty big. It's 14 pages, so we're not going to be able to cover it all in one day. So we're going to cover a little bit today, maybe a little bit on Thursday. Any that we miss out on, Cindy and Elaine, they'll be able to cover that in their class. So we'll get through all of it. But for now, we're going to focus on the Chapter 10 project. You'll find the Chapter 10 project on page 574 in your course pack. Page 574. Um, the Chapter 10 project is going to be all about hypothesis testing, but we're going to be using the data that we collected for our candy. Okay. So back in October, I guess it wasn't Halloween. I guess it was the beginning of this month we started talking about it. Um, but we're going to pull up our candy data. And then if you go to the Chapter 10 project in Canvas and you click on it, it'll bring you here, and there is a link that'll take you to random levels of significance. So you'll want to click on that, and that's going to take you to this file in StatCrunch. So let me open that up. So what does that look like? So in Canvas, you'll click on Chapter 10 Project, and then click on this link that it's going to take you over here to StatCrunch, and then you'll have to sign in. Give me a second. I thought it was signed in. I thought I was already signed in, but I'm gonna have to, it's gonna make me do it again. All right. There we go. Okay, now I'm good. All right, so page 574. Um, so use the StatCrunch file to generate two different random levels of significance. Okay. The levels of significance, that's your alpha. Okay. That's your error. Okay. You can think of it as it's the opposite of your confidence level. Okay. Last time when we were building confidence intervals, we were looking at like confidence levels that were like 90%, 95%, things like that. Alpha is the error, so it's going to be much smaller. It's going to be like 10% or 5%. Okay. So what we'll do is we'll go to that StatCrunch file and we'll click on data, sample, and then do a sample size of 2, and we'll fill those in right here. Okay. All right. So you click on Chapter 10 project in Canvas, and then you click here, and then it's going to bring you to StatCrunch. Then you go to data, sample, click on data, and then sample. And then you're going to select levels of significance. That's the column here. So, and we're going to pick two random numbers from here. So these numbers go from like 10%, 6% down to 1%. Okay. So we're just going to pick two random numbers. So your sample size here is 2, and you hit compute, and it'll fill in your numbers here. So my first one is 0.091, so 9%. And then my other level of significance is 0.023. And I'm just going to fill those in on my paper here. Okay. Um, and your numbers are going to be different from mine because you just picked two random numbers out of that list. Okay. Um, but that's fine. The project is going to give you a chance to try your own numbers. Okay. So one of these we'll use, the first one we'll use for M&Ms, the other one we'll use for Skittles. Okay. If you watch this morning's video, I had two different numbers and they were much closer together. This one's 9%, this one's 2%. This morning's video, they were both like 6%, right next to each other. That's okay. Um, all right. Which M&M color had the highest count in your sample? Fill out the table. Okay, so let's see. All right. For M&Ms, my highest count was orange. Okay. And yours will be different. That's, or maybe yours was orange too, but you probably didn't have 29. So my successes, my X value is 29. N is how many I had in my whole bag, which was 145. Okay. Next, I need P hat. So P hat is X over N. All right. So what is that going to give me? 29 divided by 145, 0 0.2, 0.2 exactly. Lucky me. All right. Willy Wonka is bothering you and claims that more than 1/6 of the M&Ms of your color, mine is orange, so more than 1/6 of all M&Ms are orange. Write the appropriate hypothesis to test Willy's claim. Note, use a fraction, not a decimal. Okay. Um, all right, so he's coming to me and he's saying that uh, there's something going on. M&Ms, they're making way too many orange. Okay. So we're going to test that and see. Now, what they should be doing is 1/6. Okay. This 1/6 is what we're going to test it against. This is our P0. Okay. So our null hypothesis, though, our null hypothesis is going to be P equals 1/6. Your null hypothesis is always equal. Okay. So all of this stuff, all of these steps, you're going to find on page 262 in your yellow exam notes packet, hypothesis for testing a single proportion. Okay. And you'll notice that there's three different ones we could do. We could do left tail, we could do right tail, we could do two-tailed, but all of them, the null hypothesis is the same. P equals P0. Okay. P0 is going to be a number. P is going to be a letter because we don't know P. We can't know P. P is the population, and you can't measure that because you can't measure the entire population, but we are going to approximate it using a sample, and we're going to basically see, is the result from our sample close to the P that we're expecting, close to this P0, or is it very far away? Okay. That's what this hypothesis testing is all about. Okay. But step one is write out your null and alternative hypothesis. So that's what we're doing here. The second page, page 263, is hypothesis testing for means. We're not going to be doing that today. Today we're focused on proportions. We're focused on what proportion of M&Ms are red, okay, or what proportion of Skittles are purple or whatever, okay? All right, so here's my null hypothesis, and then your alternative hypothesis, and you can write it as HA or you can write it as H1. Either of those is fine. Okay. Uh, and in this case, we need to decide, are we using a left tail test, right tail test, or two tail test? Now, the one-sided ones, left tail and right tail, they follow pretty much the same steps. Okay. But the two-tailed one, I mean, the steps are the same, but it does matter which one you are looking at. If you are looking at a two-tailed test, that's actually going to cut your p-value in half a bit. It's going to actually widen your z-values out. And so it does change things, okay? Down here for step 4, we're going to be calculating a p-value, okay? And then for step 5, we're comparing that p-value to our alpha, okay? If you're doing a one-tailed test, your p-value is going to be uh, a little bit, uh, it's all in one side, so it's going to push your z value a little bit closer to 0. Okay. So that matters. So when you're checking whether I need to do a two-tailed test or right-tailed test, you need to look for words like more than or less than or different. Okay. Less than is obviously left tail. More than or greater than is going to be right tail. But if it's different, we would just be looking at two tail. Okay. Anyway, for this case, he says more than, so we are going to use greater than 1/6. Okay. So this is our hypothesis and our alternative hypothesis. And like I said before, you can write it as H1 or HA. I don't care which one. If you write it as H1, that makes it feel like, oh, you have H0, then H1, H2, H3. No, you can only have one alternative hypothesis. If you're going to have more things that you're going to test against, that would be an entirely another experiment. Okay. But anyway. All right, next page is page 575. Verify whether all the requirements to conduct an appropriate test of the hypotheses above have been met. So we need to check random, independent, and okay. And these are going to be the same, very close to the same steps that we had when we were doing confidence intervals, because if the central limit theorem for statistics is satisfied, if you have these three all are yes, then you could do a lot of things. You can do confidence intervals, you could do hypothesis testing, right? So they are related, but they are different steps. So anyway, the for random we're not going to say yes given because we didn't actually know whether it was random, but we do know that we didn't pick out our M&Ms like cherry pick them. So we do know that the answer is yes here because uh, every M&M had equal chance of ending up in my sample. Okay. All right. For independent, we need to check that 20n is less than capital N. So my N was 145. I had 145 M&Ms. So this is 290. And my capital N, everybody's capital N is all M&Ms. Okay. I'm pretty sure that 2,900 is less than the number of all M&Ms in the world. So this is definitely a yes. Lastly, for normal, we need to check N times P times Q, and that has to be less than 10. Okay. Now, my N was 145. Which P do I put here? We kind of play a little fast and loose with our P because sometimes we write P, sometimes we write P hat, sometimes P zero. We'll also have P values today. These all mean different things, okay? Um, so when we're doing hypothesis testing, um, we want to be comparing to P zero, okay? So yeah, it's not a huge deal, but they're not the same, right? My P hat is 0.2. My P0 in this case is 1/6. It's what I'm comparing against, okay? When I did my sample, did my P hat come out as 1/6? No, it did not. 1/6 as a decimal. What is 1/6 as a decimal? Let's see. 1/6 is 0.1667, right? So my P hat is different from that, and that's to be expected. The question is it close? And that's what the hypothesis testing is checking is this it's definitely higher than 1/6, but is it high enough that I can say that it wouldn't matter what sample I picked, it's always going to be higher. Because, when you do a random sample, there's a chance that my number of oranges was very high this time. If I chose a different bag, a different sample, there's a chance that my p hat value would be a little bit smaller or bigger. I don't know. But the question is if I do this sample, is it likely that it's always going to be bigger? Okay, always bigger than 1/6. Because if that's the case, remember, your p hat is approximating the p value, right? So, like I said, we have a lot of different things we're looking at. We have p, we have p hat, we have p0, and these all mean different things. P hat is the population proportion, and we don't know what it is. We can't know what it is. For this case, for M&Ms, we've been assuming that the M&M company makes the same number of every single color. So we can say, oh, well, I'm pretty sure it's 1/6, but we don't know that for sure. Okay. And if we were looking at something else, like we were looking at, let's say we wanted to see how effective our new commercial is at getting people to buy our product. We don't know what that p-value or that proportion is. If I was testing a new medicine, I don't know what that is. So I calculate p hat based off of the sample. So this one's going to be a number. It's x over n. Okay. And I'm going to compare that to p0, which p0 is going to be some number that I'm picking that I think the p maybe is. Okay. And I'm going to see if I'm right or not. Okay. All right. Anyway, that all said, we want to be using p0 here. So this would be 1/6 or p null. Q null would be 5/6. So let's plug that in and see what we get. 145 times 1/6 times 5/6. Dang it. 29. Oh, no, I totally effed that. I totally screwed that up. Somehow my 5/6 got in the bottom. Don't do that. 1/6 times 5/6. There we go. 20.14. Okay. That's fine. It's still bigger than 10. So I got a yes. Anybody get less than 10? Anybody get a no here? It depends on your sample size. If your sample size was like 60, 70, somewhere around there, it's probably a no. Like if I had 65 times 1/6 times 5/6. Yeah, 65 is a no because it's less than 10. That's okay. I mean, it's not okay if we were doing this at our job or whatever. But for now, we'll move on. We could just say, regardless of whether or not the requirements were met, okay, we can test the hypotheses. Um, but we need all three of these to be yes in order for the central limit theorem uh, to be satisfied. And if it is, then it means that our hypothesis testing will be accurate. Okay. Regardless of whether or not requirements are met, test the hypotheses from number 3 using significance level 1. All right. So on page 262, we have 6 different steps here. Our first step we already did. I'm going to write it again. You don't need to, but just so we have it all on one page, P equals 1/6. Okay. And our alternative hypothesis is P is greater than 1/6. All right. 1/6 is 0.167 because we might need that. Next, we're going to write out what our alpha is. So step 2. My alpha for M&Ms is 0.091. So it's like 9%. Okay. Now, step 3, we write out our z value. We find our z value. Okay. But before we go on, so this alpha we picked a random number, okay? That's not the way that we would do this in real life if, I was working on some kind of project. I wouldn't just be like, 9%, that sounds good, okay? Um, this alpha is going to be an important conversation that you have, and it's one of the first things you do is talk about like, okay, what level of significance do we want? Because this is going to be our error rate. Now, you want your error rate to be as low as possible, okay? But that doesn't mean you always want your alpha to be low as possible, okay? To be as accurate as possible, you want to have a large sample size. We talked about that before. But if I make my alpha too big, then there's a chance that I will reject the null hypothesis when I should not have. And that's what we call a type 1 error. There are two types of errors. The other is a type 2 error, and that's where when I do not reject the null, and I should have, okay? Um, and both of those can cause major problems, right? Like if I was testing some kind of medicine and I don't reject the null hypothesis, um, then maybe I end up giving out medicine that isn't effective. Okay. So if you make your alpha too small, you risk making a type 2 error. Okay. So it's important to discuss that with whoever's, looking at these numbers. Okay. You can't just pick a random number like we did. Okay. For today, though, random number, there it is. Step 3. Step 3 is we write out this crazy formula, p hat minus p0 over the square root of p0q0 over n. Yeah. Now it looks crazy, but it's actually the same way that we calculated z values before. You take your number minus the mean, okay? In this case, we're using p0 as our estimate for the mean, for the p value, the proportion, and then divide by this standard deviation, which is this crazy square root thing, but it's the same thing. You're just dividing by the standard deviation. So, but we'll plug in the numbers we have. P hat for me is 0.2. P0 for everybody is 1/6, but I'm not going to write it as 1/6. I'm going to write it as a decimal just because I don't like having fractions inside of fractions. Yeah, I mean, even down here, we've got a fraction and a fraction. If we'd wrote 1/6 and 5/6, you'd have two fractions inside of a fraction underneath the square root. It gets out of hand. So the nice thing about this class is we don't do a lot with fractions. All right, but I do need to figure out what this is as a decimal. So my Q, 1 minus 1/6, 0.833. I mean, I like fractions, but I know some people do not. And when you are doing a story problem where you're dealing with real world things, we very rarely use uh, fractions because most people understand decimals. Most people have a hard time with fractions. So, all right. So now that I have this, I can either type this into uh, Desmos and get my z value, or I can skip this and I'll come back to it after I've done some StatCrunch. Okay. So either way is fine. I'll skip it for now. We'll come back to it and fill it back in. Don't forget, but fill in our z value in a second here. That's terrible. All right. For step 4, we're going to draw our little picture here, and I'm doing a greater than, so I'm shading in my p-value over here. Okay. This right here is z0, which, I could calculate out, get the math for it. Okay. But so, maybe it's like 2.3 or something like that. Okay. This z right here corresponds to some p-value, underneath of the normal curve. And we've been doing this for a while, like in chapter 7, where I give you a z, find the probability. Or I give you the probability, find the z, right? We've been doing that for a while. This p-value, by the way, is not the same as any of these ones. It's not p, it's not p hat. It's a different p-value. So there are a lot of p flying around, so be careful with this one. This is the number you're going to compare against alpha, okay? So maybe we should use a different letter or something. That's why we use the Greek letters, because you start to run out of symbols. If you just use P for everything, it gets confusing. So, all right. But what we're going to do for this is stat, proportion stats, one sample with summary. Okay. So you go stat, proportion stats, one sample with summary. Okay. Now that's the same steps you would do for hypothesis testing. Okay. You fill in your successes. I had 29 orange, 145 total M&Ms, but instead of clicking down here for confidence intervals, I'm going to keep this button checked for hypothesis testing. My null hypothesis, I want to compare that to 1/6, which is 0.167 or 1667. I'm doing a greater than, and that's it. So when you're doing confidence intervals, you do usually want to check this button here where it says show the critical value. Don't use that for hypothesis testing, because if you do that, it's going to confuse you. It's going to present you two different z values. Okay. So I'll show you what that would look like. So if I did this, it gives me two z values. It gives me a z stat and a critical z. So don't do that, because then you're like, which one do I write down? Okay. The one you want is the z stat. Okay. So the reason why they do that is because you might find in other classes or in other textbooks that um, you can compare your p-value to alpha, which is what we're going to be doing, or you can compare your z-stat to some critical z-value, which is tied to your alpha. You can compare those z-values, okay? And you can reject the null hypothesis or not based on that. Um, Either way is fine, but it's confusing if we talk about two different ways to do it. So we are going to just be looking at this p-value here. So my z-stat is 1.065. And my p-value is 0.1433. So I'm going to fill those in right here. So I filled in my z value. I filled in my p-value over here. Okay. So you'll notice that if I had done this as a two-tailed test, it's going to give me a different p-value. Okay. So when you're doing, if you do it as uh, one-tailed test, whether it's left or right, it's going to give you a similar p-value. Um, Not the same, but anyway. So in this case, for the two-tailed test, my p-value is actually double if I do a one-tailed test. Okay. Here I have this one-tailed test, 0.1433. Okay. If I'd done two tails, it's 0.1433 on this side and 0.1433 on the other side, which adds up to 0.28. Okay. So that means that I'm going to be rejecting the null hypothesis less often in a two-tailed test. Okay. So it's important to pay attention to that. Okay. Anyway, for this, next step, step 5, is I compare my p-value and my alpha. So mine is 0.1433. My alpha, 0.91. And you're going to have a different p-value, and you're going to have a different alpha than me, and maybe yours will be less. For step 5, if the p-value is less than alpha, you reject the null hypothesis. For me, it is not less. I have greater than. So I do not reject. We never accept the null hypothesis. We only ever reject it or do not reject it. Okay. The reason why is because, so I'm saying my null hypothesis is p equals 1/6. And here I'm saying p is greater than 1/6. In this case, I'm not saying that, oh, p is definitely 1/6. It's a yes. It's for sure. All I'm saying is I don't have enough evidence to agree with the alternative hypothesis. Um, P might still be bigger than 1/6, but in this case, it might be just a little bit bigger than 1/6. And I'm not measuring it close enough. I'm not measuring it with uh, you know, a close enough microscope. Okay. Maybe I need to reduce my alpha. Maybe I need a bigger sample size. Okay. Anyway, for this case, for me anyway, since it's greater, I do not reject it. If yours is less, you would say reject the null hypothesis. And usually that's what you're trying to do. Usually when you are looking at these kind of tests, you're hoping that you can reject the null hypothesis and use the alternative, okay? Like if I was measuring some medicine, I'm hoping that this new medicine is better, okay? Uh, and so I'm hoping that I can reject the null and we can, or if I'm looking, I made this commercial. I'm hoping that commercial is going to increase my sales. So I'm hoping it's better than it is right now. Okay. Now, that all said, just because you're hoping to get the alternative hypothesis and reject the null, you can't just, fudge your numbers. You can't just be like, oh, well, we're going to make our alpha really big because that's going to make it easy to reject the null. Okay, because by doing that, you're giving yourself a chance of making a larger chance of making an error. Okay, you can't just choose a number. Oh, let's not use 1/6. Let's use like, why don't we use like 1/10? Okay, by manufacturing your numbers, by fudging your numbers just to make sure that the test turns out in your favor, you might end up causing issues. All right. Last step is we write out the conclusion. So we're going to interpret. So this part's going to be, a sentence going to be in English. So, and it's going to be very similar whether you reject it or not. You would write either there is enough evidence, or in my case, there is not enough evidence, or sufficient. I should write sufficient. There is sufficient evidence to support the claim more than 1/6 of all M&Ms. Population is all of them. All right, let me read this. There is not sufficient evidence to support the claim that more than 1/6 of all M&Ms are orange. Okay. Did anyone end up rejecting the null hypothesis? Did anyone end up with a really small p-value?
Yeah, mine has the less than 0.0001.
Oh, wow. 0.001. Okay. Interesting. So yeah, you must have had one color that showed up a lot.
Almost half of my M&Ms were blue
What?
out of
Okay.
170 some.
Jeez. So yeah, so what our hypothesis is testing is we're trying to test whether the p-value is more than 1/6. Okay. And it might be more than 1/6. Maybe it's, you know, maybe it's 0.168. That's barely bigger. And so if it's barely bigger, you're going to have a hard time confirming that. Okay. Um, on the other hand, if the true p-value is much bigger than 1/6, like let's say it's 0.3, okay? If that's the case, then whatever sample I take, my sample ended up having, you know, 20% of my M&Ms were orange, okay? Um, but if the true p-value is far enough away from p0, then it doesn't matter what sample you take, it's always going to end up that you're going to have that color show up the most. Okay. Now, so you said half of yours were blue. Mine, I didn't have a ton of blue. So, um, what did I have? I had 26 were blue. So that's still a lot, but yeah. So in your case, you rejected the null hypothesis, and that's okay, even though, we can probably all agree that like that was just a weird bag, right? I don't think I've seen other bags that are half blue, but it can happen because we're doing a random sample. Or maybe there's some bias. Yeah, maybe we should check that. But all right. So
Maybe gas station M&Ms are just more blue.
maybe they're just more blue. Yeah. So like I said before, there's two types of errors, and by you rejecting the null, well, we can argue that, oh, you made an error. That's actually not true. The M&M company is making the same amount of every color, so it should have been 1/6. Um, but you don't know that. The error rate is going to be your alpha. So if my alpha is 9%, there's a 9% chance that I'm going to make an error. Okay. So it's pretty big, right? So maybe I want to get a smaller alpha. Okay. Okay. So whatever your alpha value was, that's what you're going to put right here. The probability of making a type 1 error. All right, let's move on. So next, page 576 is about Skittles. Which Skittles color had the lowest count in your sample? Mine was purple. I had 34 out of 241. Let's see, that's 34 divided by 240. I got 0.141. Okay. So there's a note here that if your p hat is close to 20%, 0.20, choose the color with the second lowest count and redo the table. Okay. So what do we mean by close to? So if this was like 0.19, maybe you would want to do that. Um, in my case, it's fine. Okay. If you're at 14% or even 18%, even at 19%, it's probably fine. Okay. Um, but we said a second ago, like what we're trying to do is we're trying to compare this. We're going to be comparing to 20%. 20% is 1/5. There's 5 colors of Skittles. So we're going to compare that to 1/5. Okay. Um, but if the p hat is very close to that, you're going to have a very hard time rejecting your null hypothesis. Okay. And like we said before, most of the time, rejecting the null hypothesis is the result you're hoping for. Okay. But just because that's what you're hoping for, that doesn't mean you can just you know, choose whatever numbers you want. Okay. In this case, we're allowing it. We're allowing you to say, okay, fine, pick the second lowest color. But that's bad practice. Most of the time, you use the sample that you got, and you don't just say, oh, well, this is a bad sample, so we're just gonna go ahead and use this medicine anyway. Okay? Because that could be dangerous, right? Or you spent money creating this commercial and you test it and it's actually not very effective at producing sales. You can't just say, oh, well, that was a bad sample, or that's a bit we picked a bad p-value, so we're just going to go ahead and run it and pay for the airtime, because you're going to be paying money uh for something that's not going to help your business. Okay. So anyway, all right, moving on. Willy Wonka, it keeps bothering us. So I don't know why. Willy Wonka was the good guy, right? In Charlie and the Chocolate Factory. So shouldn't it be like Hot Nose, or what was the other guy? Fickle Gruber? I don't know. Weren't they the bad candy guys? I don't remember. Uh
That's up for debate. I seen the movie.
oh yeah? You
He
say
was
what?
not very nice.
Which one was not very nice?
Willy Wonka.
Willy Wonka? Okay.
No,
All
he
right,
is
that's
not
fair.
the good guy. Natural consequences, sure, but those were children that were put in deadly
Those were children.
situations.
That's fair. Yeah, no, that's fair. You definitely put a lot of people at risk that time. All right, so he's back and he's claiming the proportion of Skittles that are, in my case, my color is purple. He's claiming that the proportion of all Skittles is different from 20%. All right, so we're gonna write out our hypotheses here. Your null hypothesis is always going to be the same. It's P equals, and he's claiming 20%, so 0.20. Okay. But your alternative hypothesis, it depends on whether it's left tail, right tail, or two-tailed. So he doesn't know if it's more than 20% or less than 20%. He's just saying that it's different. It's not 20. So he's saying, I don't know what they're doing, but they're not making the same amount of purple as every other color. Okay. So in this case, it's not equal to. And we saw a second ago that that mattered, because that means that our p-value down in step 4 is going to be twice as big. Okay. It'll make it harder to reject the null hypothesis. Okay. All right. Verify whether all the conditions to conduct an appropriate test are met. Random, independent. So, yes, every Skittle had equal chance of being selected. Sure. Independent, I need to check 20 times n. Is that less than my population size? Uh, I have 4820. Is that less than all Skittles? Yeah, it definitely is. All right, lastly, for normal, do n times p, and we're going to use p0 and q0, okay? Now, when you were doing confidence intervals, you didn't have a p0 and a q0, so you did use p hat and q hat when we were checking normal. Um, it's not a huge deal, uh, but it does make some difference. So my p0 is 20%, my q0 is going to be 80%. Okay. And the reason you didn't have a P0, Q0 when we were doing confidence intervals was because, well, we weren't testing it against a particular value. We were just saying, give me a range of values where the P is probably going to land. Okay. Here, I'm not looking for a range. I'm looking to compare it to a specific number. Is it close to 20%? All right, so I got 38.56, and that is bigger than 10. So yes. Okay. Did anybody get a no for normal? Your sample size was around 50 or 60. You might have gotten a no. I mean, uh, I guess I should ask if you got a no. I asked if you had a no for normal. I guess I should also ask, did we get a no for independent? Did you buy billions of M&Ms, or a no for random would be like you went and you just picked out the colors you liked. Anyway, I got three S's, so I'm good. But even if you have a no, regardless of whether or not the requirements are met, let's test our hypothesis. So step one, and we already wrote step one, but again, I'm gonna include it here. I'm not gonna mark you off if you don't. P equals 20%. P equals 1/5. And the alternative not equal to it. Okay. I'm gonna put my step two over here, so I'm somewhere. Alpha. All right, my alpha for Skittles is this one. All right, step three. Calculate my C value. My P hat. What was my P hat? 0.141. P0 is 0.20. Big square root. Q0 is 0.8, 80%. 241. All right. So you can do this, again, you can do this in StatCrunch, or if you want to type it in the calculator, that's fine. When you do that, you need to make sure you put parentheses around the top, and just make sure that everything in the denominator is underneath the square root. 0.20 times 0.80 by 241. And mine is negative, which is fine, 2.29. Okay. If you wanted to, you can leave that blank for the moment, and we can go over here and calculate our p-value in StatCrunch, and then fill that in after we've with the data that we get out of StatCrunch. Now I'm doing a two-tailed test, so I'm going to be shading both sides of my graph here. And if you add this shaded piece plus this shaded piece, you get your p-value that you're going to compare to alpha. Okay. All right. So, all right. So I'm going to close this one because I don't want to get mixed up with what I did for M&Ms and for Skittles. So I'm just going to close that out and just start over with stat, proportion stats, one sample with summary. And I had how many purples did I have? 34 out of 241. Comparing that to 20%, not equal. So I'm going to leave that one alone. And I'll hit compute. And you can click the p-value plot if you want. You don't have to. It just looks like this. It just looks like the graph you already drew. All right, so this z-stat is very close to the z-stat that I had, negative 2.289, but it's not exactly the same, negative 2.286. So I'll accept either one, okay? Um, but the p-value is what I want. So my p-value is 0.0222. All right, great. Step 5, I'm going to compare my p-value to my alpha, 0.0222, 0. What was my alpha? My alpha was 0.023. Wow, those are pretty close. Uh, so my p-value is just barely less than alpha. So I reject the null hypothesis. If I had made my alpha just a little bit smaller, so you remember we want to make our test as accurate as possible. We saw earlier where like I had a 9% chance of getting an error, and like Kara had half of her thing was blue, half of her thing was blue M&Ms. So if I want to be more likely to um, be accurate, I want this as small as possible, but that's going to make it hard to reject the null hypothesis. So Ivana, you have a p-value of 0.138938. No, that sounds good. Your numbers are not going to match my numbers. So you're going to have a different p-value because you had a different bag of candy. You're going to have a different alpha than me because you're going to go in and you're going to do data and do a random sample from the significance levels. You're going to basically pick two random numbers. So you might have that your p-value is bigger than alpha, in which case you would say, do not reject the null hypothesis. Mhm. All right, so then if you do reject it, you'll see there is sufficient evidence. Or if you do not reject it, you'll say there is not sufficient evidence to support the claim that, oh, it's not more than, in this case, to support the claim that uh, the proportion of all Skittles that are purple, there is sufficient evidence to support the claim that the proportion of all Skittles that are purple is not 20%. There is sufficient evidence to support the claim that the proportion of all Skittles that are purple is not 20%. Does that sound right, Cindy?
Yes, I definitely think so.
All right, sounds good. So you'll notice that my p-value was very close to my alpha. If I'd made any changes, like if I had a smaller sample size, I probably would have not rejected it, okay? Or if I'd made my alpha smaller, okay? Um, or you know, if I did this sample again, uh, and my bag ended up with just one less sorry, one more purple, um, then it would have probably flipped. Okay. So, uh, so I think that's interesting. So, because usually what you're trying to do is you're trying to, you're hoping to reject the null hypothesis. Um, but just because you're hoping to doesn't mean you can engineer it that way. I can't just be like, oh, well, let's not compare it to 20%. Let's compare it to 21%. Okay. By the way, here, uh, I did not write that it's more than or less than 20%. I just know that it's not 20%. Okay. So there is a chance that the true p-value is in either tail. So even though my p hat was 0.141, which is definitely less than 20%, there is a chance that I just got a crazy bag and actually it's more than that. Okay. That's the difference with a two-tail test. Okay. So, all right. Anyway, when you are setting up your hypothesis testing in the same conversation that you're talking about, okay, what alpha should we be setting? You would also have that conversation with your boss or whatever. Uh, does it matter if it's more than or less than? So like if I'm testing a commercial, I want it to be more than. I want it to be more likely to have people buy something from my store. Okay. Um, but uh, you can't just be like, oh, well, that didn't work. So I'm gonna just flip it from being a two-tail test and make it a one-tail test now. Okay. That that is something you would address at the start, not after you've done your sample. All right. Question 11. Which test had a higher chance of a type 1 error in the setup? So your alphas, your levels of significance, that is the chance that you have a type 1 error. Okay. So my M&M one was 0.091. My Skittles was 0.023. So whichever one of those is bigger, that's the one that had a higher chance of a type 1 error. Type 1 error is where you um, you reject the null hypothesis, but you should not have. You reject the null hypothesis, but the null hypothesis was actually true. Okay. I know like I said, we always want to, or not always, but usually you want to reject the null hypothesis. Um, but just because you want it doesn't mean that's the case. Okay. All right. Um, So yours might be different, by the way. You're going to circle whichever one of those is higher. So if your Skittles one was higher than your M&Ms, you circle that one instead. Okay. All right. Question 12. Which test had a higher chance of a type 1 error in the setup? That's the same question. Which test had a higher chance of a type 1 error? That's yeah, okay, so that's the same question. Um, I think so last time we ran this, this was type 2. Um, I but I pointed out to Alana, you can't ask that in this class. We haven't talked about it. So I think she tried to correct that, but ended up just making it the exact same question. So the the chance of a type 1 error is alpha, okay? Which we've been talking about. The chance of a type 2 error is beta. And we haven't talked about beta. Uh, we're not going to. We're not going to calculate beta in this class. So when I asked which test had a higher chance of a type 2 error, I can't answer that. Okay. I can say that beta is related to alpha. If you have a large alpha, you'll have a small beta. That's mostly going to be true if your sample sizes are the same. Okay. Because beta is not just based on alpha, it's also based on your sample size. Okay. If you have a small sample size, beta will be large. Okay. So my M&Ms, I had a sample size of 100, 145, but I had way more Skittles. Not double, but almost double. And so um, it's possible that I have a higher chance of a type 2 error and have a higher chance of a type 1 error on M&Ms. Now, most likely that's not the case because this alpha is very different from this alpha. Okay. So a small alpha usually means a big beta. So it's probably this one. But if these were much closer, if you watch this morning's video, if this is like 9% and this one's like 8%, a bigger sample size is actually going to cause less error for type 2 as well. So it is possible that you can cause errors on more likely to have a type 1 and more likely to have a type 2. Okay. Beta is known as the power of a test. Okay. Like I said, we are for the most part not going to worry about that. Um, what's a good alpha? Again, it depends on what you're trying to do. If we were talking about medicine where it's life and death, like, you don't necessarily want to just pick a random number. We're looking at candy. We're looking at M&Ms and M's and Skittles. So sure, pick a random number. It doesn't matter. Okay. Um, but a good alpha is somewhere between like 10% and 1%. A good beta, a good power of a test is um I, sorry, beta is 1 minus the power. Totally effed that up. Good power of a test is like 80%, so a good beta is like 20%. Okay. Anyway, that all said, you can answer whatever you want for number 12. I'll give you so it's free points. Free points. Sorry about that, guys. But the good news is that is the end of the chapter 10 project. Make sure you submit that. And before you leave for the night, we're going to do one page out of the sample final. So the sample final exam is on page 605. And like I said, it's big. It's 14 pages, so we're not going to do it all the night. We're definitely not going to do it all right before the final exam, but I do want to do a little bit at a time so you get through all of it. So, because it is worth points. So page 605, following box plot shows the percent of a state's residents who are Hispanic, classified by region, West, South, Northeast, and Midwest. All right. What is the shape of the distribution for the South region? So here's the South one. So skew left, symmetric, or skew right?
Skewed left.
Okay. Um, and why? Why do you think that?
Most of the data is to the left of the mean.
Yeah, so the middle line right here is the median, and you have a big box here to the left, and you have a big tail here to the left. So I'm okay with that. But I will point out that I have two outliers over here to the right, and those are actually going to drag it up. So I'm not really a fan of this question. We just did question number 12 with beta, and wasn't a fan of that question. Same thing here. These outliers, if these outliers are big enough, it could actually be skewed right. So again, I'm going to give you points for whatever you pick for answering. Free points again. So if it's a little skewed left and a little skewed right, maybe it's symmetric. Nah, but I like your reasoning, Kara. Since this box here, I don't know why they didn't pick, they should have picked West. This is clearly a bigger box here and a bigger box here, and you don't have outliers messing it up. Anyway, whatever. But your reasoning
I
is
also didn't
is
even
is
see the
valid.
outliers when I answered.
Yeah, yeah. So they were kind of hidden, right? So they're not obvious. But yeah, those dots out there are outliers for that row. Okay. If we had the mean and the median, we could compare those. All right. Oh God. Based on your answer from part A. Oh my God. We're off to a rough start. Here we go. Which would be the best measure of spread and center to report for the Hispanic percentage of the South region? So if it is skewed left, we want to use the median and the interquartile range. Okay. Um, Now, we even talked about median and interquartile range for a while. Chapter 7, 8, 9, 10, we've been talking about mean and standard deviation. Okay. Um, Median and interquartile range, they're not affected by outliers and things that are skewed as much. Um, but why have we been talking about mean and standard deviation? Well, the central limit theorem says that if you have a big enough sample size, you satisfy the central limit theorem requirements, then any sample that you take, the sample distribution is going to be normal, which is symmetric. And in that case, you're better off using the mean and standard deviation because they have more power. I know we said we weren't going to talk about beta, but beta is the probability you make a type 2 error, and a test that has more power is going to be more accurate. So you're better off using these when you can. Okay. So anyway, you are allowed to do hypothesis testing with the median and the interquartile range. It just gets a little weird because it's not done very often because it's not as powerful of a test. All right. Which region had the largest average? Now, average for this class it usually is mean, okay? But for this case, we're really just looking at the center, which is the median. The median is the center line here. So which of them had a highest center line? So this one's at like maybe like 13. This one's at like 12. This one's way down here. So I think it's west. Whichever of these center lines is farthest to the left. All right. Which region had the smallest range? So the range is from the minimum all the way to the maximum, how wide that is. Now this one looks like it's very small, a very small range, but it's from the minimum to the maximum, and this outlier out here is actually the maximum. Okay. So the smallest range is the Midwest. All right, this one's for you guys. Which region had the largest spread?
The West,
Yeah.
even with the South's outliers, it's still larger.
Yeah, and that's because when we're looking at the interquartile range, we don't worry about the outliers. We're looking at the width of the box. And so this box is very wide. This box is small, so you got it. All right. 50% of Northeast states had Hispanic percentages above what? What do you think? Sounds good. So the Northeast is right here. So it's like 12%, 12.5, somewhere in that area. Maybe, I think it's like, it could be 11.5, maybe. I don't know. All right. What percent of Western states had Hispanic percentages below 28.7? So 28.7 is right about here. And we want to look at Western states. So that's right here. This spot right here, this line is called the third quartile. What percent is below the third quartile? If you have 3/4, how much money do you have? You have 75 cents, right? 75%. All right. Florida in the South has the highest, oh, sorry, second highest Hispanic percentage at what? So here's South. Um, Highest is this dot. So second highest is going to be this one. So that one is Florida. So what do you think that is? It's like 27, 26. I'm not going to be crazy like this, like 28.7. Sure, 26%. Kara says 27%. That sounds good. 26 point, maybe, okay, maybe 26.5, sure, but okay. All right, we're going to stop here for tonight. We'll work more on the sample final exam hopefully next time. Uh, But if anyone has questions, feel free to stay on. Otherwise,
Are
uh, Cindy, we'll see you tomorrow.
are the chapter 3 notes due on Thursday or were they supposed to be due yesterday? In Canvas, they have the due date set to the 17th.
Okay, 1 second. For the 10.3 lecture notes. I'm sorry about that. I will get that fixed right now. So if you turned them in already, great. If not, you have until um, the end of the night. So yeah, I apologize for that. Yeah, 17th was Monday. Oh no, sorry, not tonight. The 20th. It should be the 20th. Yeah, there we go. I think I got it fixed. There we go. Due on Thursday.
I think everybody's gone.
Okay, that's fine. I don't have anything else.
No,
So,
I'm good too.
all right.
Besides
Have a
my
good night,
voice.
Cindy.
Yep, you
Oh,
too, Joe.
my voice is bad too.
Oh my goodness. Alrighty,
Mm.
I will see you on Thursday.
All right, bye.